Hello, I'm Dave Brown for Teletrain. Today we continue our discussion of solid-state electronics with Chapter 3, which is entitled Rectifiers and Power Supplies. In the last chapter, you saw how a diode functions as a half-wave rectifier. Another type of rectifier is the center tap rectifier or full-wave rectifier. A transformer is necessary for this rectifier circuit, and 2 diodes are required instead of 1. During the positive half cycle, diode 1 will be forward biased, conducting, but diode 2 will be reverse biased and not conducting, or cut off. During the negative half cycle, diode 1 will be cut off and diode 2 will be conducting. This repeats for each half cycle, so the output voltage will be like this. We still have pulsating DC, but the pulse rate is now 120 hertz when the power line frequency is 60 hertz. For the center tap full wave rectifier circuit, a center tap transformer and 2 diodes are required. But this circuit has the advantage of a high output voltage. As we will see later, it's easier to smooth or filter the voltage to obtain pure DC. Power supplies of this type are used in high-quality radios, television sets, and stereos. Still another type of rectifier circuit is the full-wave bridge rectifier. The diodes are arranged in a bridge configuration, which means they are arranged in a square, as you see here. During the positive half cycle, diodes 1 and 3 are forward biased and therefore conducting. Diodes 2 and 4 are reverse biased and do not conduct. We have a positive output pulse. During the negative half cycle, diodes 1 and 3 are reverse biased and do not conduct. Diodes 2 and 4 are forward biased and are conducting, which gives another positive pulse. The bridge rectifier provides pulsating DC with the pulse rate at 120 hertz when the input is 60 hertz AC. This is the same as the center tapped or full wave rectifier. The bridge rectifier circuit has the advantage of obtaining a full wave rectification without a transformer, but has the disadvantage of requiring 4 diodes. Also, care must be exercised when using this rectifier without a transformer to prevent shock hazards. Careful circuit design and careful selection of grounding points must be observed, or one leg of the bridge can be shorted out, which would reduce it to a half-wave rectifier. The bridge rectifier is widely used in instrumentation circuits, particularly in meters used to meter AC. The AC is converted into DC by the bridge rectifier, and a DC meter is used to indicate the AC voltage. Diodes are rated according to the current which can flow through the diode without damaging the diode. This rating is expressed in maximum current, or by stating maximum power that the diode can dissipate. Diodes come in different sizes and shapes. The more current the diode is designed to carry, the larger it must be. The reason for this is that the junction in the diode will have some resistance. Even though this resistance is small, when the current flows through the diode, Ohm's law tells us a voltage drop will occur across the junction. When we have a voltage drop across a resistance, we will also have power or heat produced. The amount of power or heat produced is determined by the formula P equals EI. The voltage drop multiplied by the current. You can easily see that the heat produced will increase when the current increases. This heat must be removed from the diode, or the diode will be damaged or burned out. For small values of current, the heat can be radiated into the surrounding air. For larger currents, where there is more heat, It is often not possible to radiate the heat into the air fast enough to prevent damage to the diode. It is necessary to remove the heat in some other way. A common way is to make the diode with a screw or stud attached to the case and use the stud to fasten the diode to a metal object, usually the chassis. The heat produced in the diode is conducted away from the diode into the chassis. The chassis is used as a heat sink. Since one conductor of the diode is attached to the stud and therefore to the chassis, care must be exercised in the circuit design in order to prevent short circuits to ground. A way to prevent these short circuits is to use a thin mica or plastic washer to insulate the diode from the ground. The insulation washer must be thin so as to not interfere too much with the heat conduction. For larger currents, special heat sinks are used. These heat sinks are made from a good heat-conducting material, such as aluminum, and have fins made into them to get maximum radiating surface. For high current rectifiers, fans are often used to blow air across the fins of the heat sinks to remove the heat. We said earlier that when a diode is used as a rectifier to produce DC from AC, we have pulsating DC. For many applications, this pulsating DC is not satisfactory, and pure DC is required. The pulsating DC can be smoothed by a filter to obtain a steady value of DC. A simple filter would be to connect a capacitor across the output of the power supply, like this. As the value of the pulsating DC increases, the capacitor will charge during the increases in voltage until the voltage across the capacitor is equal to the peak value of the pulse. The voltage from the diode will start to decrease, but the voltage stored in the charged capacitor will keep the voltage more or less constant. Some of the voltage stored in the capacitor will be used by the load resistor, so the output voltage will not remain at the peak value, but will drop somewhat. During the next half cycle, the capacitor will again charge to peak value, and the cycle will repeat. The voltage from the power supply without a capacitor for a filter looks like this, and with a capacitor for a filter, it looks like this. The small up and down variations are called ripples. A single capacitor filter is not sufficient for most applications. A resistor can be added which will give us a better filter. This filter is called an L-type filter, since it resembles the capital letter L turned sideways. We can add another resistor and form a T-type filter. It is called a T-type filter because it resembles the letter T. We can arrange the components and have a pi-type filter, called a pi-type filter since it resembles the Greek letter pi. All these filters are RC filters, since the circuit components are resistors and capacitors. If we replace the resistors with a choke or inductor, we will have LC filters. The L is the symbol used for inductance. We can have L-type LC filters, T-type LC filters, or pi-type LC filters. All these filters will result in a lower ripple on the output voltage. These filters can replace the single capacitor in our circuit like this. This is an L-type, this is a T-type, and this is a pi-type. There are several special purpose diodes. One of the most common is the Zener diode. The Zener diode has the unique characteristic of maintaining a constant voltage across it. Therefore, it can be used to regulate the output power supply to keep a constant DC output voltage, even if the input voltage changes somewhat. So far, we've been concerned with the diode, which is a rectifier in which the p-n junction is composed of p-type and n-type germanium or silicon. Some other materials also exhibit the semiconductor effect caused by the sharing of electrons in the outer shells. Some metallic oxides have the semiconductor effect, and two of these materials are copper oxide and selenium oxide. Copper oxide rectifiers have been used for many years in battery chargers and other applications where a direct current, or DC, must be obtained from alternating current, or AC. Selenium rectifiers have been used for many applications in radio and electronics. Copper oxide, selenium oxide, and some other materials share the property of being sensitive to rays of light. When light is focused on the junction, the resistance of the junction will decrease. The brighter the light, the lower the junction resistance. These p-n junctions, which are sensitive to light, are called photodiodes. If we connect the photodiode in a circuit like this, with the p-n junction reverse biased, that is, with the negative battery terminal to the p-type material and the positive battery terminal to the n-type material, the amount of reverse current will be determined by the amount of light on the junction. For dark conditions, very little reverse current will flow, but if we illuminate the junction with a bright light, the reverse current will increase. Applications of the photodiode include some photographic light meters and some automatic door openers. When light is focused on some p-n junctions, a voltage will result, and we call this the photovoltaic effect. These diodes are called photocells. There is considerable interest in the use of photocells, or solar cells as they are called, for producing electricity. Each p-n junction, or solar cell, will produce about 1/2 volt at a very low current. So it will take many, many solar cells connected in series and parallel to produce very much electricity. However, solar cells have been used to provide power for satellites, even for large satellites like Skylab. The large wings on Skylab were covered with solar cells. Solar cells are used in many applications, not as exotic as satellites circling the Earth. Some industrial light measuring instruments and some photographic light meters use solar cells to determine the light level present. Solar cells are also used in control circuits. We have seen that some p-n junctions are sensitive to the application of light. Some other p-n junctions will emit light when a current is passed through them. Remember that electrons and holes pass across the junction when a current flows through the junction. In the area very near the junction, some of these holes and electrons recombine and energy will be released. In an ordinary diode, this energy is given off as heat. In diodes made of materials such as gallium arsenide phosphide and gallium phosphide, the energy is given off or emitted in the form of light. These diodes are called light-emitting diodes, or LEDs. When we apply a voltage, the diode will conduct and emit light. The diodes can be arranged to form numerals or letters. The diodes in this indicating device are arranged to represent numerals. By applying voltage to the proper terminals on the back, the numerals 0 to 9 will result. LEDs can be made in very small sizes and low power requirements, which make possible the digital watch and handheld calculators. The use of LEDs is very common today, with many digital indicators such as clocks, digital voltmeters, laboratory and industrial instruments, and automotive applications. That's it.